Okay, so now today we would like to talk about chapter 12. Chapter 12, multiple integration. So in chapter 11 we talk about partial derivative, and actually we consider this in this kind of function g equals f of x y. It's a function contains two variables. More, of course, it could contain more variables, but we focus on two variables. Yeah, we focus on this one, and we could define it by g equals f of x y. Then we have the graph about, for its graph is something like this study, is something like this one. And for example, g equals x squared plus y squared, something like this form, right? And for this kind of function, it contains two variables or more than two variables. Then we consider its derivative. And when we consider its derivative, we have a name. I mean, we consider it partial derivative, partial g, partial x, or partial g, partial y, right? And when we consider its derivative, or you could read it this way, it's our, for the function originally we should write in this way. I mean, for this function it's in the form f of x y. This one. For this function, when we consider its derivative, partial derivative, we write this way. It's this one, this one, or this one. And this one is to differentiate by x, and this one is to differentiate by y. And as we say, there is one important concept. Is that when we consider this one, differentiate by x, then we could view y as constant. It's an important concept. And when we consider the function is derivative by y, then we could view x as constant. It's an important concept in chapter 11. Okay? Yeah. And once we have partial x or partial x y, then we could solve lots of proposition. We have lots of results. Actually, almost all results are related to partial derivative. So it plays an important role in the differentiation when we talk about a function which contains two variables or more variables. Okay, and then since we have already considered differentiation, now we consider integration. Okay, so it's called multiple integration. And the multiple integration, there are some results in this chapter. So I think due to time, we will focus. I think at least you should know the result in section 12.1. And it's the case, double integral over rectangle. Rectangle is defined on rectangle. And actually in next section, we talk about a similar thing, but it's over any region. It's in section 12.2. If we have time, we could talk some about the result in section 12.2. But for you to prepare your final exam for chapter 12, you should prepare the result in section 12.1. Yeah. At least you should know the double integral over rectangle. And okay, so now I will tell you double rectangle. What does it mean? And before I tell you double integral, I would like to tell you, actually we have a nice result. The nice result say that originally we have double integral is definition, but if we want to solve a question, for example, if I give you a question, okay, so for example, if I give you, okay, you will better to give you the example once I introduce the definition. Yeah. Anyway, so double integral, I will tell you the definition, but originally, if I want to solve a question, we won't use the definition directly. We will use a nice result, I mean Fubini theorem. And the theorem says that originally we want to solve it by double integral, but it also means that we could solve it by repeat integral. Repeat integral, if you just see the form, you will see for the function, we integrate by y here. For this function, we integrate by y firstly, right? So for this form, we integrate by y firstly, and after that we integrate by x. After that we integrate by x. So in this case, if we integrate by y, it means that we should fix x. Later we will tell you this case and this case, that case, and their geometric meaning. But just in this form, I want to explain some. For this form, for this function, it contains two variables. But for this function, if I say this one, integrate this function by y, then we fix x. So you could view x as a constant. So it's something like this one, right? In this case, we view x as a constant to consider its derivative. And this one, once you see this form, we integrate by y. So we fix. Sorry, there is something wrong. dy dx. So here it should be. We fix y. Oh yeah, sorry. Here we fix y. Sorry. Here x and y. Okay. Yeah. So we fix y. Here we fix y. And then we fix y means that y, you could view y as a constant. Y just a constant. Yeah, y is just a constant. Okay, so you will see that we will use some similar argument or similar idea or similar way to solve this kind of question. I mean, as the case when we consider partial derivative with respect to x, then vy is a constant. And now consider integrate this function by x, and we also view y as a constant. And then in this case, it's the same. Okay, so now I tell you the graph. I mean, tell you the definition and what do they mean. Okay, so before I tell you the double integral, let's recall the definition about integral. So in chapter 5, we say that if I give you a function y equals f of s, integral of the function f, and we integrate it from a to b, it means that it's the area of the region. And which region? The region is above the x-axis, below the curve, and s between a and b. So we have a region. For this region, its area is this one. Its area. Okay. And then for its area, what's the definition? The definition is that now we separate. So we divide it into n subinterval. And in each subinterval, it has the width delta xi. So now we divide it into n subinterval. So we have s0, s1 until sn, and the s0 is our a, sn is our b. And yeah, and we could consider simple case. I mean, divide it by n subinterval, n equal subinterval. So delta si is equal to the subtract the difference, but it's all since they have the same width. I mean, n equal subinterval, so it's equal to b subtract a over n. So the height, each one. The height. So we just choose si star from. Si star between si star is greater than si subtract 1 less than si. Between si subtract 1 and si. And for sample point, we consider its height f of xi star, and it's the height of this rectangle. So we have f of xi star. It's the height of the rectangle, and for the rectangle we have the height and we have width. We have the width. But actually we divide it into n subintervals, so actually we have n equals n rectangle. So we have n rectangle. So actually we have n rectangle. And with that n approach infinity. And that is the definition. Okay, and that is the definition. And it means that below the curve y equals f of s, up above the x-axis, and the x between a and b, and the x between a and b. Okay. And then now let's see what does double integral mean. And then now we consider a function which contains two variables. So its graph is this one. Here it becomes originally it's a curve. Now it becomes a surface. It's a surface. Okay, it has a surface. And then now we consider a case where its domain is a rectangle. Its domain R is a rectangle. Here the domain is AB interval, an interval. But now the domain, since we have two variables, so its domain becomes two variables. So here it becomes a rectangle. In this case, it's rectangle case, and in next section is the any region case. Okay, so it's rectangle. So, but we use similar argument. I mean, for the AB, we also divide it into n subintervals. So we have x0, x1 until xn, and x0 is our A, xn is our B. This one, and y0, y1 until yn, and it's our C, and it's our D. This one. Okay, and xi star between xi subtract 1 and xi, and the yj star between yj subtract 1 and less than yj. Okay, and we also have delta xi. Delta xi is the subtraction. We divide it into n subinterval, and the CD for the interval CD we divide it into n subinterval. For CD we divide it into n subinterval, and for AB we divide it into n subinterval. Here n subinterval, and here n subinterval. So and delta xi means delta s is the difference, and the total length is b subtract a, but we should divide by n, so it's b subtract a divided by n. And delta yj total length is d subtract c, and then we should divide by n. Okay, so what's the definition? The definition means that so now we have the delta aij. Delta aij is the area. The area is equal to delta xi times delta yj, and all of them are the same. So here we have this part is the delta aij, and delta aij means that it's equal to delta xi times delta yj. Delta aij is the area. So and here this part is the area, and we multiply by height. So we have an area of a rectangle here, and for the rectangle we consider volume. Which volume? We choose one point xi star between xi subtract 1 and xi, and choose another point yj star between yj subtract 1 and yj, and we consider its height f of xi star yj star, and consider its rectangular box. Yeah, we have a rectangular box. So here we consider so for its volume. The height is f of xi star yj star. And then area is the height, right? It's the height. And here is the area, the area. And the area equals delta is the area. And the area equals delta SI times delta YJ. This one. And we have here we divide it into n subinterval. So we have n. So we should consider all of their sum. J goes from 1 to n, I goes from 1 to n. And finally, let n approach infinity. Let n approach infinity. And then it's our definition. Okay, so it's our definition. About double integral. So what does it mean? In the graph? It means, okay, so I just explain again. Here we have a rectangle. We have the region R. It's a rectangle. And the function is defined on the rectangle. And x between a and b, we divide it into n subinterval. And y is between c and d, and we divide it into n subinterval, equal subinterval. And for each one, so now this part, so now we have n times n rectangle, and each one their area. Each one their area equals delta xi times delta yj. And delta xi is this one, delta yj is this one. And for the height, we consider one sample point, si star, yj star, si star between these two values, yj star between these two values, and we have one point over here, and consider its height, and we consider a rectangle, the rectangular box. The rectangular box its volume is the height times the area, right? And we should consider all of their sum, n times n, and then approach infinity. So its meaning is that we consider the volume of the solid, and which solid? The solid is below this surface, g equals f of s1, below this surface, and above xy plane, and s between a and b, y between c and d. Okay, s between a and b, y between c and d, and above the xy plane, and below the g equals f of sy. Here it's above the x-axis, below the function y equals f of x. Okay, so that's the different part. Okay, but it's there is some similar part, yeah, between them. Anyway, okay, and when we solve this kind of question, okay, so now we talk about next one, repeat integral. And so here I erase some because it contains too many words. So I erase some, keep the main form. Otherwise I erase it, just keep this form. Okay. Yeah, so now as we see in chapter 5, if I ask you the question s squared dx, s goes from 0 to 1, will you solve it by the definition, original definition? I just erase it. Will you solve it by definition? Actually, we won't, right? We will use fundamental theorem of calculus to solve it, right? And for this one, double integral, if I give you a function, for example, here is s squared plus y squared dA. This function is our f of x, y, and s between 0 and 1, y between 0 and 1. This one is our region R. This one. We consider its integral, double integral. How to solve it? By definition? No, by definition it's complicated. Just like single variable function. If you want to solve it by definition, it's complicated. So how to solve it? We will consider the next one, repeat integral. And repeat integral originally is just explain it by just here for the graph, just to explain what it means. But there is one important result. It's called Fubini theorem. And the Fubini theorem says that original want to solve it by double integral, but it's equal to repeat integral. It's equal to this one, and it's also equal to this one. If f is a nice function, for example, continuous function, and in this section, and actually for most questions you will see the nice function. For example, the continuous function, for example, like polynomial or trigonometric function or exponential function, natural log, all of them are continuous function on their domain. So they are nice functions, so you could use this result directly. And later I will write down the result, Fubini theorem. Anyway, so now let's see another one. Repeat integral. We will solve it by repeat integral. We will solve the equation by repeat integral. So now let's see repeat integral. What do they mean for these two notation? What do they mean? First one is we integrate it by y, integrate the function f by y firstly, and after that integrate by x. And this one is integrate by x firstly, and after that integrate by y. And now let's see the difference. Okay, so now let's see the difference. Here, if we integrate by y, it means that we fix x, right? Then, so you could view x as a constant. So what does it mean? We fix x. For example, here we consider this one, and we fix x. For example, we let x be 2. Then we let x be 2. Then here we let x be 2. Then now we consider this. Line. We consider a plane s equals 2, and the surface g equals f of sy. S equals 2, g equals f of sy. Then we have an intersection here, right? It's an intersection, and in this intersection, it's a line, and then in each point in this intersection, its x coordinate value. Must be 2, right? Its x coordinate value must be 2, and the y coordinate value, y is some value between c and d. Y is some number between c and d. And the g equals f of 2y. So each point in this line, its coordinate is this one, 3-dimensional coordinate is this one, 2y, f of 2y, right? And actually this line is g equals f of 2y. If we let x be 2, then it's exactly f of 2y. So now, indeed, you could view it as just a single function, and its variable is y. So of course you could consider f of 2y dy, right? And then y goes from c to d to integrate this area. Y goes from c to d. This one. You could consider it's integral. Indeed, you could consider it's integral. So what does it mean? It means this area. Is equal to A2. It means this area, the area of this region, right? But this area, the area of this region is dependent. It's depend on x. It's depend on the number 2, right? So if we change the variable x, then its area will change. So it's a function, and whose variable is x. So now we integrate by x, and we integrate the function x. So now you could view it as a function of x. Now it's a function of x. So we integrate it and dx. So it's better to sorry. Here is fixed x. So you could view with fixed x. So x is constant, and for this part you could view it this way. It's ax. So here is equal to integral ab dx. This one. X. So for this function, it's a function whose variable is x. And so now we integrate e by x, and x goes from a to b. X goes from a to b. So it's called repeat integral. Repeat integral. Repeat integral. And by Fubini theorem, the result is say it's equal to the value of v. It's equal to the value of v. This one, double integral. And then it's the result Fubini. It's the result Fubini. Fubini says that it's equal to its double integral. This result. This one is by Fubini theorem. We know that this form is equal to double integral. This one. And now let's see this part. Now let's see this part. Here is fixed x, fixed y. Means that we could view y as a constant. And now the difference. Now, what can we say? Here now we fix here inside we fix y. So we could view y as a constant. For example, we let y be 2. Let y be 2. Now we consider the plane y equals 2, and the surface g equals f of xy. Then it has the intersection here. It has the intersection this line. It has the intersection this line. It has the intersection this line. And then in this line, each point, its y coordinate value is 2. So it's of the form x 2 g equals f of xy, f of x2. Right? In each point in this line, its coordinate, its three-dimensional coordinate is this one. Okay, and this line you also could say that it satisfies g equals f of x2. This one, g equals f of x2. And of course, for this line, you could integrate by x. So for this line, f of x2, of course you could integrate by x. And x goes from a to b. Indeed, you could consider this one, right? And what does it mean? It means a of 2, the area of this region. When y equals 2, the area of this region, I just use the green color. Okay, so it's exactly equal to A2. It's the A2 region, its area. And in general case, it's AY. Right? It's our AY, and we integrate from C to D by the variable y. This one. Okay. So for this repeat integral, we integrate by y firstly, and after that integrate by x. And when you integrate by y, we should view x as a constant with fixed x. And here we integrate by x firstly, and after that we integrate by y. So when you integrate by x, you should view y as a constant. Okay, and again, it's equal to, actually by Fubini theorem, it's also equal to the volume V. And here for this result we call it Fubini. And then we said I will write down the theorem soon, later, yeah. Okay. So that's why I say there is one important thing you should know. I mean, for example, give you a quick example. For example, f of sy equals s squared y. Then as we say, when we consider this one, s squared y, it's partial derivative. But with respect to x, then what's this? You should view y as a constant. So just consider s squared is derivative. And its derivative is 2x. So the solution is 2xy, right? This one. And then now we integrate by x. If we integrate by x, what does it mean? It means we can say x squared y integrate by x. This one. If we just integrate by x, so then we view y as a constant. So x squared, it comes from x cubed, right? X cubed. Y is a constant, keep it. But this time x cubed is derivative is 3x squared, so we should divide by 3. This one, this one, this form. If we don't have any bound, then it's of the form, then it's this one. If we don't have any bound, then the solution is this one. Okay, so they have some similar concept. They have some similar concept. When we say partial derivative, and now we say repeat integral, they have some similar concept. Okay. Yeah. Okay, so now I will write down the Fubini series and give you several examples, and finally tell you one concrete example, which I mean, it will be related to the geometric meaning. Okay. Later, let's see the example. I will tell you more.